Okay, get started. Hello everyone, I'm Dongdong, a PhD student from Columbia University. Today I'm going to talk about a learning-based fuzzer called NEUZZ. NEUZZ is based on a neural network model and perform efficient gradient guiding mutation. Fuzzing is becoming a popular way to find software vulnerabilities. In the last 10 years, the number of fuzzing papers has been growing a lot. Many researchers are trying to make fuzzer more efficient. However, almost all of them are variants of the same design, evolutionary fuzzing. Evolutionary fuzzing starts with the initial seed. Then through random mutation, it generates multiple child seeds, then select the one with the most promising result as the initial seed for next round. Evolution techniques are easy to implement and have shown significant promise, but it is not very efficient. Since the random mutation not very effective and wastes a lot of mutation without valid guidance, they tend to get stuck after a while running. In practice, it is hard to find scalable and adaptive heuristic for guided mutations. Many prior work try to address this limitation in different way, but without changing the fundamental fuzzing architecture. In this work, we consider fuzzing from a new perspective, an optimization problem. That is to find a set of X to maximize the number of sum shown here. Capital X represents all possible input space. Lowercase x indicate a program input, and fx denotes the number of bugs yielded by execution of specified input. Most of the inputs will simply return 0 on fx, since bugs are hard to find and only can be triggered by a small number of real inputs. Cx is a sample function to generate k inputs restricted by fuzzing budget from input space. A fuzzing campaign often has a resource limit, such as time budget and computation budget. Thus, it can only be generate a fixed number of mutations within this budget. And the aim of such optimization is to find a set of inputs which uncover the maximum number of bugs within the fixed resource budget. However, such function fx is ill-behaved because it is discrete and mostly contain a lot of flat plateau, and sharp transitions make it really hard to optimize efficiently. Function fx is actually an impulse function and has two spikes, x1 and x2. Recall that fx represents number of bugs found by a particular input. From the graph, we can see that for the target program, only 2 inputs can yield abnormal budgie behavior, while other inputs just trigger normal behavior and yield no bugs. As for any sample function cx, it will be extremely hard to generate k inputs which happen to hit x1 and x2. So to solve this problem, modern fuzzers turn to an easier target, edge coverage, rather than number of bugs. Simply because, in practice, the more edge a fuzzer can explore, the more likely it can uncover a bug. We define gx as the number of edges taken during execution of input on target program. And the object function right now tends to maximize the total number of edges by finding an optimal set of input x. Now we have gx, a step function representing edge coverage. Many inputs have some edge coverage. Compared with prior one, this function gx is easier to optimize since it contains more states and more transitions between them. Evolutionary technique is a popular way to optimize the function gx to achieve the maximized edge coverage. Here is an example. Evolutionary optimization starts from initial set, say 0.1, then perform random mutation. Since the random mutation has no any valid guidance, the resulting mutant can be any point and only depends on luck to hit any interest region. Then it reaches 0.2 and check whether it introduces any new edge coverage. If it doesn't, the initial set still stay at 0.1. Then reach 0.3, no edge coverage, reach 0.4. This time it's lucky. It find new edge coverage, so the SID changed to 0.4. However, since the random mutation can easily cause the new input to jump back into no gain region, like this, we could have 0.5. Note that this example is a simplified one-dimension input space, while in the real-world cases, the input can have as large as total input length dimension, where random mutation is not efficient. To provide more guidance in mutation, we propose a new approach, gradient-guided optimization. It has two steps. First, we smooth approximate the objective function. Second, we compute gradient of the smooth function we just approximated, and further perform efficient gradient-guided mutation. Assuming somehow, magically, we could obtain a smooth approximation of Gx, like this. Hx is a smooth approximation of Gx. Then we compute gradient of Hx to obtain promising direction and focus mutating on this direction. Similar to last example, we start from 0.1. Then we compute gradient, and we came 0.2. Compute gradient, go to 0.3, then 0.4 to 0.5. Following the gradient, we're approaching the spark error or the interest error and achieve higher edge coverage than evolutionary method. Gradient guide optimization seems pretty promising, but the problem is how do we smoothly approximate Gx, while the objective function Gx has no explicit analytical form. Moreover, it is only accessible from a black box manner. That is, we can only get the output, that is the edge coverage of Gx, through lightweight instrumentation of target program. According to universal approximation theorem, a single hidden layer neural network model can approximate any continuous function. Thus, the neural network is a natural fit to this task. Our solution is to use a neural network model to smooth approximate Gx, and our learned function is Hx. After obtaining the smooth approximation, then we perform gradient guided mutation. The first question I want to ask is, why gradient guidance? Well, we compute gradient of edges with respect to input. The gradient represents the importance for every byte in the input. By choosing the input bytes with the largest gradient value, we can identify the critical parts. Then, what are the critical parts of input? In reality, only a small fraction of input determine program branches. This small fraction of inputs are critical parts of input. How it works? Once we identify the critical parts of input, we can greatly reduce the searching space and focus mutating on this location, hence improve the fuzzing efficiency. Now let's look at the main idea of NEUZZ. Given the program and feed input, it will execute and trigger a corresponding path composed of a set of control flow edges. This set of control flow edges are program's branching behavior for the specified input. Then we train a neural network model as the smooth surrogate of program that will take in the same input and predict the same branching behavior. A nice property of this smooth surrogate is the differentiability. A program composed of the CPU instructions is not differentiable, while a neural network surrogate is differentiable. Thus, we could compute gradient of branches with respect to input and perform efficient gradient guiding mutations. Here, we will peek into the neural network model to explain more detail of the training. Program inputs like a file or string can be considered as a byte sequence, each byte with value range from 0 to 255. So we can represent the byte sequence with a numerical vector. Then we fit the input into target program and obtain the branching behavior. The branching behavior consists of set of control flow edges taken during dynamic execution. If edge is taken, it is marked as 1, else it is marked with 0. We use program inputs as training data X and the edge bitmap as training label Y to train a neural network model which learn a function to predict the dynamic branching behavior for a given input. After training of the neural network model, a question popped up that how it generalizes to unseen branches. Our observation is that most program inputs of real-world program are highly structured, and this structure of input form as the critical parts of input. Program logic mainly focuses on the critical parts of input and parse them to trigger different program branches. Our solution is to identify critical parts of input from observed branches and use them to help explore unseen branches. In this graph, we show the overall design of NEUZZ. NEUZZ starts with a set of seed coppers as initial training data. Then it uses a neural network model to learn a smooth surrogate of target program. After the training, NEUZZ compute gradient of edges with respect to inputs and perform efficient gradient guiding mutations. Further, we will keep the mutated inputs that cover new edges and add them into our training dataset. Since the initial dataset only covered partial program space, we keep refining our neural network model with incremental learning. Our evaluation consists of 4 parts: real-world program, LLaVA-M, and DARPA-CGC dataset, comparison with RNN-based fuzzer, and performance of different model choice. We evaluate NEUZZ on edge coverage against 5 state-of-the-art fuzzer, including FL, ClearFL fuzzer, FFuzz, and FL left intel. The evaluations performed on 10 real-world applications for 24 hours running, cover 6 popular file formats, including ELF binary, JPEG picture,